This video is about CTMU and how it fits in with Einstein's theories of special and general relativity. So we're gonna just go briefly into what that is. So essentially, what the principle of relativity, which was not discovered by Einstein, was discovered by Galileo, says is that all motion is relative. Essentially, all things move with respect or relative to the position of all other things in the universe. So you can't really say what is moving relative to what. So if you're on an airplane, that moves relative to the Earth, but the Earth is also moving relative to the plane, depending on your perspective, whether you're on the plane or on the Earth. And this leads to some funny conclusions, which is that, for example, the track moves faster for Usain Bolt than for his competitors, at least from his inertial frame of reference. An inertial frame of reference it's a stationary perspective where an object won't change speed or direction unless acted upon by an outside force. And the laws of nature, which are Newton's laws of motion, there are a couple others, are the same for all inertial frames of reference. And one of those laws is the speed of light, which always travels at the same speed. So the speed of light is the same for all inertial frames of reference. And I don't know that this would necessarily be known to Einstein, but the reason for this in the CTMU is that light is a generalization of information because it carries information about objects to perceptors. So the processing speed, of the conspansive manifold, which is reality. Conspansion is inner expansion, and requantization, we'll get that later, occurs at the speed of light. It's just the invariant speed which was set for the conspansive manifold to conspand, which is a function of information. So as we get close to the speed of processing, things start to lag in a sense. It takes more time for the same functions and operations and descriptions. But we'll get into that later. So Einstein was the first person to notice that these first two principles contradict each other. Because the speed of light should be different. If I'm traveling at 20 miles an hour faster than someone, then light should appear 20 miles per hour slower for me, but it doesn't. So anything traveling at the speed of light will have the same value for its speed for all inertial observers, and this appears to be at least in conflict with the principle of relativity. So a way to think about this is if I have a mission controller on the ground and I have a spaceship, and the spaceship flashes a light down, and the light obviously goes at the speed of light. But the spaceship is also traveling parallel to the ground at 3/5 the speed of light. The spaceship is 3 feet above the is 4 feet above the mission controller. Then in the time when the spaceship's has traveled 5 meters, then the light also will travel 4 meters instead of the initial 4. So the time from the missions controller's perspective for the light to reach the ground is 4 over c, 4 over the speed of light, 4 sec. Whereas the time for astronaut is 5 over c. So the astronaut moves 3 meters in the time that the light travels 5. So that means she's going at 3/5 the speed of light. So actually, what relativity says, and this is a very counterintuitive conclusion, is that time actually slows down relative to relative to the observer. So everything going on inside the spacecraft is slowing down. It's not just the it's a distance for the light to reach the ground or perception. It's the the clock, the workings of the electronics, her aging process, her brain activity are all slowed down at the same speed. At the same ratio if they're going the same speed. It's actually slowed down. Just using the Pythagorean theorem, we know that it's slowed down by a factor of 4/5 at 3/5 the speed of light. And it slows down exponentially faster as you get closer to the speed of light. So that's the first important aspect. The next thing is that is the idea of a world line, or the fourth dimension. So, essentially what Einstein says is that everyone is tracing out a world line with 4 coordinates. It's 2 spatial dimensions and 1 temporal dimension. So he adjoins time as the 4th dimension, which is correct. And this is counterintuitive, we'll just say that what we see usually is a 2-dimensional representation, and this solves the problem of relativity. So what we see is a 2-dimensional representation of objects at right angles to our eyes, which actually exist in 3 dimensions. So if I have a pencil and I have 2 people looking at it from 2 perspectives, they'll disagree over the length of the object from their perspectives, but this is fine because we know that sight is a 2D flattening of 3 dimensions. So the 3D, so if you take into account that third dimension and their different perspectives, there's actually nothing is amiss. They're just looking at the same. The pencil is. They trust that there is an objective pencil which exists in 3 dimensions, and we can see this kind of using our depth perception because our eyes are at different locations. But that's just for the sake of example. So in the same way, the 3D distance that we measure is just a 3-dimensional projection of 4D reality. So relativity says, or special relativity says, that observers in relative motions have different viewpoints and thus observe different projections of 4D reality. So there's another important concept. It's an event. So an event is something that happens at a certain point in 3D space and at a certain instant in time. So in space, lines join contiguous points. In space-time, world lines join contiguous events. So this is why Chris Langan refers to space-time object triality. There's space. So to identify the position of something, you need to know its coordinates in space, its coordinates in time, and what it is. It's the object. So we said that that our perception from 3 dimensions, which is what we experience, is a flattening of 4D reality. So the question emerges: what is that 4D reality? So this is when we venture from physics to metaphysics, because we're actually talking about reality in some fundamental sense when we're talking about what all of our perceptions are embedded within. So the problem, this is what William James, who was a psychologist, he observed with Einstein's theory, is it's not a technical problem, but is that he calls the model, which is induced from special relativity, he calls it the blocked universe, because in 4D nothing changes because past, present, and future exist on equal grounding. So not only does all of space exist at each point in time, but all of time exists at each point in space. So this leads to a purely deterministic, conception of the universe, because that we just happen to be experiencing at this one point, but all things, are already there's no real difference between past, present, and future. The CTMU comes along and he says, that's not quite true, because the future only exists only as, unbound potential, as unbound telesis, which is then bound by tellers, which is bound by causation, the highest order of which is God, which, regenerates reality at every instant. And then humans who have, we have local free will, and then objects which have, aren't really free, but they have, kind of self-modeling capacities. They can sustain themselves in some sense by reading information about past states and then collapsing potential into a new state according to its syntax. So this is what the syntax state feedback loop described in the CTMU. But so what the CTMU does, it embeds the block universe it embeds special relativity in ultimate reality, such that it is no longer a formal theory set apart from its universe. Because the block universe doesn't have back to, if you watch our Leibniz video, there's the principle of sufficient reason, is that something has to be distinguished from its logical counterpart in order to come into being. So the block universe doesn't have enough structure or processes to bring itself into being. It has no reason to exist. Its purposes are not embedded within itself. So the block universe, while it explains certain phenomena with respect to relativity, is inadequate to explain its own existence, operations, and descriptions, and thus fails to qualify as a true theory of everything. And Einstein himself acknowledged this, not in those exact terms, but he never claimed to have a theory of everything, and because it's inconsistent with quantum mechanics, or at least what we've observed about quantum mechanics. But as a self-aware, self-referential system, which as an ontology couples essence and existence and brings itself and self-generates both as its theory model and formal universe, the CTMU bridges this gap and is able to complete Einstein's mission of working to understand the fundamental nature of reality and explain the behavior of the universe at a global level. So that was pretty important. So what it says is, instead of being a block universe, it's what Chris Langman calls the conspansive manifold. So the conspansive manifold is it's a dynamic structure, and it's a mathematical structure that represents the fundamental nature of reality as it evolves over time. It's a multi-dimensional space which encompasses all possible states of the universe, and the dynamics of the manifold determine the evolution of the universe. But they are not predetermined, they're self-determined. They're determined in real time. So it's essentially, you can think about this as the block universe dipped in God, is a funny way of putting it. Back to what we were talking about earlier, the C invariant. So we showed that the faster one travels, the more time slows down. So the speed of light is constant. It's impossible to pass it because you'd reach infinite mass. And so then what Einstein gets from that is possibly his most famous equation, because it's not the easiest to understand, but it's the easiest to say. His most famous concept is E equals mc squared. So as an object increases in speed, it acquires kinetic energy, which increases its mass. And as velocity approaches the speed of light, mass increases to infinity. So additional force won't increase the speed of the object. But what E equals mc squared showed us is that mass, when you generalize it, when you actually extract, what is matter, what is mass, it's actually more fundamentally, it's energy. Energy is the fundamental substance of the universe. But what the CTMU says is, in some sense, this is right, but it's actually the more fundamental substance is actually telesis, which is a metaphysical generalization of energy and information. So energy is that which energy is the material substance, and then information is that which essentially organizes the material substances. So this is the two phases of conspansion, which is how the conspansive manifold, which is a generalization of the block universe, but these are the two phases of conspansion, which is how the conspansive manifold evolves over time, are internal expansion, so that's the energy, and then requantization. So there's an influx of energy, and then the information distributes that to where it should go according to the causation determined by God, by humans, and by particles, and by itself. So that's how the universe evolves over time. It's not in a deterministic way, it's in a self-deterministic way, which allows a model for free will, both among humans, self-generative freedom, which is free will, which is generalization of free will, among God, and, very, very local free will among particles, enough to distribute certain generic properties to generate the universe, but not enough for decision making, let's say. So that's special relativity. We're not going to go too deep on general relativity because it's more complicated. But essentially, so what general relativity says is all objects fall to the ground at the same rate in a vacuum. So this was known, but essentially, it's almost like gravity knows to pull one object harder and one lighter to reach a constant acceleration of 9.8 meters per second squared. But what the one moment. So the gravity and acceleration. But what Chris Langan says about this is the in the CTMU, gravity does indeed arise. Gravity is real. But in the CTMU, gravity does indeed arise through the telic principle, which means it's a function of teleology for the purposes of the evolution of the real universe. But it's as a property of the conspansive manifold rather than as a force. So that's why there's actually cognition behind it, and it knows how hard to pull. The universe knows, essentially, given an object's mass, how hard to pull on it, given relative to another object's mass. So the emergent property of gravity as a property of the conspansive manifold. So out of that arises, the emergent properties which arise out of that fundamental thing is, gravitational lensing, gravitational redshift of light, singularities, black holes, and we might cover these topics in future series. General relativity led to the discovery of the Big Bang, which is another theory which needs some updating, although it isn't necessarily incorrect. So we might go over that in the future. But for the time being, it suffices to say that the CTMU essentially couples general relativity with creationism to give a complete account of the genesis of the universe, and we'll also we'll also discuss how Einstein's theory of general relativity unify, and how the CTMU unifies relativity with the modern developments in quantum theory, and how this all points the way to a fresh and exciting understanding of God, consciousness, the origin and purpose of the universe, and the fundamental laws of physics, and thus a unified theory of reality, which is actually the same as its universe. It describes the operations and descriptions occurring within its formal universe, and thus is actually the first thing which can lay the claim to absolute truth, or as a theory of everything. So that's all for today. We'll go into a fun fact that the man who coined the term black hole, which is something which is discovered as part of general relativity later, John Wheeler actually expressed interest in Chris Langan and the CTMU. And Chris Langan's papers John Wheeler's papers include several key CTMU concepts, including the participatory universe and the universe as a self-excited circuit. And Wheeler is actually cited 15 times in Chris Langan's magnum opus, his 2002 paper, which is introduced the CTMU, called the Cognitive Theoretic Model of the Universe, a New Kind of Reality Theory. And when asked by Kurt Jaimungal on the Theories of Everything podcast what advice he would give to his younger self, it was, quote, meet with John Wheeler. But the light shineth forth in the darkness. Like and subscribe for more CTMU content. Peace, truth, love, out.